Spohn, whom I don't need to introduce, I guess. And he will talk about universality classes of the Popov-Schütz two-lane ASAP. So please, Herbert, floor is yours.
Thank you very much. I mean, thank you for organizing this exciting conference, and it's always a great pleasure to be back at the Raman Institute. I mean, it's just a beautiful location and interesting science. So I guess I'm going to follow the example of Abhishek that, before doing any motivation why I want to study this, I just want to explain you the model. I mean, this is this Popov-Schütz model, and then we will see how things go. Okay, so let me just start in the middle. So this is a two-lane problem. So when you look at the top picture, I mean, up here in condensed matter, this is typically called a ladder. I mean, for obvious reasons. But anyway, I mean, so you have these two lanes, and there's no tumbling. I mean, there is running, but also there's no exchange between the two lanes. Okay, so we have obviously two conserved quantities. Particles, there is the exclusion rule. I mean, particles cannot be on top of each other. So the eta particles are sitting out of the sort of component one particles. They're sitting on the top lane. I mean, they can never jump to the other one, and the same one for the lane down below. Okay. The jumps are always nearest neighbors, so it looks sort of like a minimal extension of RSEP models which you know of, and you just, instead of having one single lane, I mean, you two lanes. Okay, so now I have to explain you the weights. I mean, that requires a little bit of attention, but it's important. Otherwise, I mean, you don't really understand what I'm trying to tell you. So let's first think about the weights for the eta. Okay. So it does a forward jump, but when doing the forward jump, it will look to the other lane. And depending on what it sees on the other lane, it will sort of have a particular weight, right? I mean, so you have you have four possible environments, and for each one of them, I put the most general case. I mean, you have sort of weights alpha, beta, gamma, and delta, right? And so it looks, and then, whatever, this occupation happens to be at the time, I mean, this is the jump rate. All right, is that fair enough? Okay, so now it's really RSEP, so you can, of course, do also, I mean, these are the right jumps, you can do the left jumps, and of course, it's exactly the same rule. I mean, now I have some other parameters which I call alpha tilde, beta, and gamma tilde. So, when you do the counting, I mean, you see that I have a sort of three model parameters which, at some point I will have to adjust, but at the moment, I mean, just look at the general case. All right, so now what do we do about the other lane? And that's sort of, well, you will see in a second more clearly, but that's sort of an important trick, and without that, I wouldn't be able to say anything sort of, of great interest. So the idea is that the weights of the lower lane, I mean, the lane 2, are actually obtained by point reflection. Okay, so let me just tell you how this works. I mean, so here is one example, and so I'm doing the jump for the upper lane, and when I look at the table, I mean, then you see that this would go with the weight gamma. I mean, it's this case over here. All right, and now I do the point reflection. So it's really at the middle of this point, and these two particles were sitting over here, and the forward jump becomes sort of a backward jump on this side. And then, of course, this is, I don't know, I was asleep when I wrote this slide. I mean, so this, of course, goes also with the weight gamma, right? I mean, just don't get confused. Okay, so this is what I mean. So by reflection, all the weights of the second component are already fixed. All right. All right. So now they looked at this a long time ago. And, one thing which you do, or at least try to do, the first thing is you try to see whether you can sort of find the invariant measures for that kind of system, right? I mean, so you let the system run, and you hope that it goes. Of course, you have two conservation laws, so you fix the densities, and then for given densities, I mean, you ask, whether you can get a steady state, and this is sort of what Popkov and Schütz actually managed, this is their result. I mean, so you have three equations which you have to satisfy. I mean, so here they are sitting on top, right? I mean, we have to satisfy these three equations, and then what they say is that under this condition, you will have essentially sort of a Bernoulli type of steady state, but still with some correlations. I mean, so here I've written down the singles. Okay, so you should think about the rungs, right? I mean, this is sort of the parts of the ladder, right? So I gave rung sort of, has a fixed label J, and so for the lattice label J, I mean, they are independent, but the two sides of the rung are actually correlated. So you see, you have sort of two parameters here. I mean, these are two chemical potentials by which you can sort of control the densities. And then you have this interaction term, which is sort of, very simple, but it's a correlation, okay? And so the assertion is that if these conditions are satisfied, this particular type of product measure is invariant, and presumably it's sort of an if and only if. But anyway, I mean, we just need this property, okay? So it's independent with respect to the lattice variable, but it's correlated for a given rung. Okay? And later on, I mean, we will actually adjust these chemical potentials in such a way that you have half filling. So both lanes are sort of, have a density 1/2. But I mean, this will come in a second. Anyway, so now I have three equations, so we are left with 5 parameters. Okay? All right. Now, I put here the eta and the theta, not to confuse you at the beginning, but it's more convenient to really talk about 1 and 2. And so, I sort of, now I call eta, what I called eta before is sort of eta 1, and the theta is the eta 2. I mean, that makes the labeling much easier. Okay, so now you have the steady state. I mean, fine. I mean, then you can sort of compute the flux for given densities of the component alpha, right? I mean, so you have the steady state. I mean, you have just to do the average over the weights, and then you get this particular function. Because we have this special symmetry, you immediately conclude that if I know the current function of the one component, I will also know the current function of the second component. It's just the negative and the interchange of the two densities. That just comes from that symmetry which I told you at the beginning. Okay? All right. So what is the next step in the analysis typically? I mean, you want to know something about the flux Jacobian. I mean, that's sort of, in some sense, the most elementary sort of dynamical property which you could look at, which is sort of this particular matrix. I mean, you just take, the alpha current and you differentiate it with respect to the two densities. Now, this is not a symmetric matrix. I mean, but you can check that, it's sort of a general principle that it's sort of a stability property which is true for essentially any system you can think of. That the eigenvalues of this Jacobian are actually real. And physically, what they mean are the normal mode velocities. So if you make a little perturbation, and then you see how the perturbation spread, then we have now here a 2x2 matrix, so we'll have two eigenvalues. It will give you two sound speeds, and you will see these two peaks sort of moving. I mean, so here you should think of having fixed, one of these steady states, a small perturbation. Of course, at the beginning, let's say at the origin, at the beginning, they're sort of a little mixed up, but then eventually they separate. This is sort of a particular linear combination of the 1 and 2 component, and equally this one. This comes from the eigenvectors. And, generically, and certainly in this model, I mean, you will find that the two eigenvalues are distinct, and therefore what you will see are sort of two peaks which are traveling with distinct velocities. So if I wait long enough, I mean, they will be separated by an enormous amount. And then you would think that, I mean, it's not completely obvious, but it's a matter of fact that, when you wait long enough, I mean, essentially, this is sort of governed by what we know from the single component RCEP. And so we know that, while they are sort of moving ballistically, the spreading of these peaks is super diffusive. I mean, that's sort of this KPC 2/3 exponent. And of course, it's sort of super diffusive for both components, but there could be special values where, the situation is sort of a little bit more complicated and you get sort of Levy distributions and things like that. But anyway, I mean, this is something which is extremely well studied, and it is not in the focus of my talk. I would like to have a situation where these two peaks have exactly the same velocity. And in our case, I mean, this velocity is equal to 0. And this can be achieved, I do really have to do a fine tuning. This can be achieved only if I put half filling. So from now on, I always think about half filling, okay? And for half filling, I mean, this picture is wrong. I mean, these two things are just sitting on top of each other, and so they strongly interact. And the question is, what is the result of that interaction? Okay. All right. So it's only a density 1/2 when the eigenvalues sort of coincide. For the rest of the phase diagram, if I change the densities, you will always see this kind of situation. Okay. So now let's see what we can say. Now comes why study, okay? So, what has been in the literature is maybe not so much this discrete model, but actually the continuum equation. So I've written down here, so the standard form of these equations. I mean, so you see here, I mean, it looks very special, but I'm just telling you what people have studied, right? And, rather than having some, a general set of parameters, they have studied this very particular case. Okay, so you see here two control parameters, that's the x and y. And here you see sort of this bilinear term, h1 and h2. This is written in terms of the height functions. And of course, for the lattice gases, maybe it would be more natural to actually look at the spatial derivative of these functions. But, this is sort of one-to-one, and I will also use the other picture later on. Anyway, so you have this one component here, and this one is sort of kept equal to 1. And here you see the diffusive term and the noise. The noise is sort of space-time white noise, and it's independent, right? I mean, so it's this set of coupled equation which sort of has sort of received some attention. And I list here you sort of, there's a very early paper by Erdős and Kadar. He was thinking about something like a stretched polymer. So you have a stretched polymer, in a 3-dimensional sitting in a fluid. And the two components, he argued that the two components, sort of the two lateral components of this polymer would be sort of well described by this kind of equation. And he did early numerical simulations on this model, right? Well, he did also actually a one-loop computation anyway. I mean, so this is quite some time back. And then this model resurfaced in the work of Jacobo Denardis. So he was interested in something totally different. Namely, he looked at the quantum Heisenberg model at the isotropic point. So this is XXX spin 1/2 chain. And then, he was sort of trying to figure out what are the spin correlations in this model. And I mean, this is already sort of a few years back. I mean, it was an exciting moment when people realized that these spin correlations are actually in the KPC universality class. Okay, so then people try to sort of produce sort of approximate. I mean, you cannot. I mean, it's an integrable model, but to actually compute this function, I mean, it seems to be extremely difficult and has not been really accomplished. But so you have sort of approximation, and then I'm not telling you the detail. I just want to say that at the end of the approximation, he came up exactly with this type of equation. However, in his case, I mean, these two parameters were equal. When x was equal to y, and then he tried to understand this equation. He did some numerical simulations. And another beautiful paper is by Weinberger. I mean, he studied directly from this case. I mean, he comes from a sort of, he's more linked to a experimental group. I mean, he comes from nonlinear optics. I mean, they can sort of, do amazing things by sort of, having materials fine-tuned. And in particular, what they can do is they can sort of produce pretty well something like, which is described by the Gauss-Pitayevsky equation. So that's a nonlinear, cubic nonlinear Schrödinger equation. So this is nonlinear optics, right? I mean, And then apparently there are also, so they can make sort of one-dimensional sort of extended systems. So they have sort of like physical models, physical realizations of the one-component KPC equation. I mean, with some constraints which I don't want to go into, but apparently they are able to also produce a sort of two lanes next to each other, and physically, they look just the same. So that they must have this exchange symmetry. And so he realized that if you impose a general equation and on top of this you impose this exchange symmetry, you end up with this kind of coupled equations. Anyway, so there are three sort of good motivations why to look at this model. And here, we produced several papers on this with the group at ICTS. And I mean, the one which I'm explaining you is sort of hypothesis on archive. And later on, I mean, you will see simulations from this group, but when this is going to come. Okay. So, so now let's see how much we can say. Okay. So, okay. So the next thing is maybe we can look at the TASEP. I mean, that sort of looks like always sort of a nice simplification. And in the TASEP, you know, all the tildes are zero. I mean, you do only forward jumps, okay? And then you can look at how many freedoms you have, and then it turns out that you know, you have already three equations, right? I mean, so somehow there's not too much freedom, and you know that there's a single weight gamma which you can do. I mean, so you put all the weights. I mean, you fix the time scale. You put all the weights equal to 1. And the only one which is different from 1 is sort of, you know, this particular sort of picture here, right? I mean, this is the weight gamma, and all other weights are 1. And the gamma you figure out is related, you know, to this correlator, which is e to the nu, and we are using typically another parameter which is q, but you know, it's sort of whatever you use. I mean, you have this one parameter here, right? Okay. And now the claim is that all the RCEPs are in the same universality class as the TASEP. I mean, this you would somehow think it should be like this, but it's actually you know, a supported argument. And so let me explain you a little bit how this goes. I mean, so we're working at density 1/2. And then the usual philosophy is that, you know, if you want to capture these kind of space-time correlations, it should suffice to do a second-order expansion relative to the steady states, right? I mean, so here the steady states density are 1/2, and so what I have to do is a second-order expansion away from 1/2, okay? And so this is what I've written for you here. I mean, so I put 1/2 plus u1. But you should think of an expansion. I mean, of course, you know, I mean, you will not get such a simple formula if I look at the general function. But if I imagine that u1 and u2 are small, then I get something which is this particular form. And you know, I put here only component 1 because the component 2 I know automatically. And the structure is the following. I mean, so first of all, you know, even if you, I mean, you know, even if in the steady state there is some net current which I call here C, and then the linear term is exactly the flux Jacobian. And I told you that you know the eigenvalues are 0, and therefore there's no linear term. But then you get this sort of funny-looking quadratic term. So you have the u1 squared, you know, the squared u2 and u1 squared, and also the cross term. But the point is that in this expression, all the other coefficients have disappeared. You see, it's only the a minus a alpha, which sort of, that's just the time scale. So if you believe that the second order is already, you know, a good enough approximation in order to understand the long-time behavior, then this argument tells you that you know, all the RCEPs must behave exactly like the TASEP. And so from now on, I will just look at the TASEP. I mean, because by this argument, the other ones sort of have lost in interest, so to speak. Okay. Now comes the question of the observables. And you know, this is a little bit biased by what we did. I mean, Weinberger looks at somewhat different observables, and you know, we somehow started with these observables and just continued, and they are not so unnatural. So we just look at this dynamic correlator, which is just sort of the space-time correlation of the two components. And Q sort of should remind you that, you know, I have somewhere fixed, you know, this weight gamma, so you know, I look at a particular state which has, you know, a particular value of nu. Okay, then here this is just a truncation. And then, of course, you know, there's a static correlator, which is sort of this object at time t equals 0. And, you know, this you see, it's sort of this delta correlate, right? I mean, it's a delta in J, but there's a non-trivial correlation with respect to the two components. Okay, so now comes an important point in this business. You see, you want to compare different models. And in order to do this comparison, you somehow, you know, you have to sort of, well, let's say you have to use some sort of coordinate system, so to speak, right? I mean, you know, I mean, if I just take, you know, the coefficients there, I mean, this is not a good way of doing the comparison. And so the idea of the comparison is that, you know, I can compare two models only if they have the exactly same static correlator. And, you know, since, you know, I can renormalize the fields easily, we always want to compare models in such a way that the static correlator is the unit matrix. Okay? So this is, so to speak, our standard. Okay? And so how do you, well, I mean, you have this matrix C. How do you do that? Well, I mean, you know, you realize it's actually, of course, it's a symmetric matrix. You do a pi over 4 rotation, and then it becomes diagonal, and then you do a dilation, and then you get the diagonal matrix. And so, you know, we have to do this kind of trivial transformations, but if you don't do that, I mean, you know, there's no way of doing a proper analysis. Okay? All right, so okay, so now comes the issue of you know, what we mean by universality. Okay, and so since I'm looking at this very specific observable, what I mean by universality is that you know, there's a universal shape. Well, there's a universal dynamical exponent which tells you how these peaks are spreading, and you know, there's also a shape function or scaling function. Okay, and so let me see. Okay, well, I mean, there's a special case, you know, where Q is equal to 0. Then you have two independent intercepts. I mean, then of course, you know, the scaling exponent will be 3/2, and you know, the scaling function is the one which we computed some time ago. So if Q is different, it should be 0. Well, you know, basically we only can do Monte Carlo simulations, and we have sort of done two types of simulations. I mean, we actually, you know, simulated the Schütz model, but we also simulated the coupled Burgers equation, which once is the coupled KPC equation. So just to have this kind of comparison. Anyway, so now you look at, you know, how many unknowns you have. I mean, there's particle hole symmetry. So this gives you that the S11 and the S22 must be the same. And also this you know, this cross correlator has to be the same. So basically, you only have to deal with two coefficients. Now, if you do this this normalization condition, then what this does to you is that once you have done this rotation and dilation, then the cross term of the static dynamic correlator is actually 0. And you only have to look at the two diagonal things. Right? So we're looking, you know, when you see the numerical simulation, you will see always two pictures, one for the 1,1 and the other one for the 2,2. And this one is sort of trivially 0. Okay, and so here, you know, just to be on the safe side, we just make this the general sort of scaling assumption, right? I mean, so the alpha will scale as j over t to the 1 over c over some dynamical exponent, which would be 3/2 for the one component system. And this one appears because, you know, it's a conservation law, and therefore the sum over all j has to be independent of time. And so you must put this factor in front. And then there's some yet unknown scaling function. Okay? So when I make this sort of assumption, then of course, you know, since I don't know very little about the system, you have to expect that the scaling exponent, I mean the C is actually depending on Q, and you have to expect that also the scaling function is depending on Q. Okay? And so if you want to decide, I mean one way is sort of to look at numerical simulations. And so our early result was, we mostly studied the scaling function, and I show you in a second. I mean, it was very clear that the scaling function is changing as I change the Q parameter or the gamma parameter. Okay? So at gamma equal to 1, I have the independent case. I see the KPC scaling function, and then it deforms sort of more or less continuously, but it cannot be fit by the KPC function anymore. Okay, so the second result is a little bit more tricky, and then I put here questions mark, and we will see why. So in our work, we basically fitted everything with the 3/2 exponent, right? And that sort of seemed to be pretty good. But then you have these simulations of Johannes Schmidt and company, and they pointed out that we should maybe look at a slightly longer time. And so I'm not sure which picture I have as the next one. Ah, yeah, okay. So this is first telling you that the scaling function is changing with Q. I mean, forget about these labels. I mean, it's sort of not so important. I mean, the main point is that here we put at -1 and -1. I mean, just to have for fun. Presumably this is not the KPC function, but there's no obvious symmetry. But this is the S11 and that's the S22, and they look pretty much the same. I mean, when you look at this thing, presumably they are really the same, right? I mean, but it's not when you try to do the fitting with the KPC scaling function. I mean, it doesn't work so well. Okay, but then I mean, this you could say a very fine effect. But when you go to some other parameter, then you see that there's a really drastic change. You see, this is sort of a little bit fatter and rather broad up here. And then when you look at the height, I mean, here you see it's 0.16, and here it's sort of much lower. So it's clear that the idea to fit this with what we know from the one-component system is not such a good idea. Okay, now we have sort of the more intriguing pictures. I mean, so these are the simulations of the second group, which I mentioned to you. And so what they did is they looked at fairly long times. I mean, so you see this is already 100,000. I mean, our simulations were maybe something around this point here, but they sort of went much further. And here you see the plot of S11 and S22, and they have done already this rotation, right? Otherwise, it would look not very, very messy, right? I mean, and then, well, I mean, okay, so you see this function, and you see it sort of nice, smoothly. I mean, so this is here they put explicitly the 3/2 dynamical scaling. Okay, and so you see that it converges. And when you look at this picture, you would like to say it should sort of converge to something, right? But we don't know. Okay. And top one is even easier. I mean, here the convergence sort of in the opposite direction, and again, I mean, you might think that if you could go even longer, I mean, maybe it settles. Anyways, so then of course you do what you should do. I mean, you say, okay, maybe it's not 3/2, but the different scaling exponent. And so, this is now doing a fit with some other scaling exponent where the numerical numbers are down here. I mean, it's almost sort of, I mean, it's close to 3/2, but it is different. Okay? And so the question is, I mean, scaling function, I think the simulations are obvious that it's really depending on your parameters for the dynamical exponents, maybe yes or maybe no, right? I mean, so we need more theory in order to I mean, more simulations looks difficult to me, but I think more theory might be able, and maybe it can sort of give some illumination. Okay, so let's see what else I want to share. Okay, so let's see how that is. Yeah, okay. So now I want to sort of switch a little back from that particular model and sort of try to sort of think about you know, what is the general picture which we developed, okay? And so now I'm going back to this coupled KPC equations, which we also simulated. I mean, you know, I mean, also the Schmidt and company did simulations actually of the continuum equations, and then they saw the same pictures, right? I mean, so in that respect, I think that, you know, the idea that you can make this sort of somewhat naive approximation, I mean, seems to work very well. Anyway, so here's a sort of, I put it also on the blackboard, I mean, so that you can see it. Here is sort of the picture. I mean, so here you have this equation, here you have the two parameters, and here I plotted sort of, you know, the x-y plane here. Now, if you are if x times y is negative, then actually the solutions are unstable, and this you can see in the Weinberger paper. I mean, it just looks totally different from what I was telling you. You know, you get all kind of interesting stuff. I mean, Priesters and anyway, I mean, it looks just sort of, it looks very different. I mean, so and this I don't have to say anything. So I mean, let's look at this sort of x and y in the quadrant 1. I mean, so here's the point which you know. I mean, this is decoupling, and then there things are just two Tarseps. Now there is this Kohl-Hopf line, which is sort of the line x equal to 1, and maybe there's no proof, but you know, there's a very, very convincing argument coming from directed polymers that if I sort of wait long times, eventually it will go to the case where both components are decoupled, and you have the Tarsep scaling functions. Okay, so what about the rest of the diagram? Well, you know, if you work out a little bit more the formula which I showed you, and then you do this transformation, then you see that, you know, the coefficient x is actually equal to 1, and also the y is equal to 1. But now, you know, the nonlinearity is sitting in this part. Now you have to sort of rewrite the equations. I mean, you know, there's a lot of sort of redundancy of how you write the equation. But if you believe me, I mean, then, you know, you actually can sort of, you know, do these extra steps. Then, you know, as I change this parameter, you're sitting always on this line. I mean, so you know, as you change q, I mean, you're sort of moving up on this line. And you can also get to the negative, but you know, maybe numerically it's not so accessible. Anyway, so the point is that you know, what you that when you look at the RCEP, I mean, you know, it never will go into the full plane. It just will move along this diagonal. Now, why is this sort of almost expected? I mean, so, you know, the reason is that when I do the x equal y, you know, it's a very special case, namely when I take x equal to y, so I'm somewhere on this diagonal, then in fact you know that for the continuum equations, the invariant measures is uncorrelated spatial white noise, right? And so you see, for the RCEP, you know, when I do a little bit of scaling, it's also spatial white noise, right? It's just independent, and you know, it tells you that if I do the rescaling, it will look like a white noise, and therefore it's clear that somehow, you know, that you know, if the RCEP would end up somewhere over here, there will be something inconsistent. Okay. So, but that's actually the case. I mean, it's just over here. Now, of course, you can try to argue, you know, what's happening if I at some other point. I mean, of course, the Kohl-Hopf line I know, but maybe I take a line over here. What is actually going to happen? Now, you see that the argument is the following. Okay, the assumption is that we don't know the steady state, but the assumption is that the steady state still is short-range correlated. Now, if it is short-range correlated and we do some sort of spatial coarsening, then, you know, very likely it will be just spatial white noise, Gaussian white noise. I mean, this is sort of what happens in any sort of decent statistical mechanics system. When I look in the high temperature phase, of course, it's, you know, and on a larger scale, it looks like white noise. Okay, so but then, you know, if it is white noise, and if nothing drastic happens to this equation, then after rescaling, you must end up on this line. Why so? Because it's only on this line that you have the white noise as invariant measure. You see, if it would end up somewhere over here, then it would be something some other measure which is simply not what follows under the assumption that the steady state is sort of short-range correlated. Okay, so now, so the conclusion is that this diagonal is a line of fixed point. Okay, so wherever you start, and if you do the rescaling, you end up at some point on this diagonal. And the question which remains, which of course is the most difficult question, is at what point do you end up? I mean, I start here, and then where do you go after rescaling? I mean, I think it's very safe to say that you go on the diagonal, but which point, I mean, we don't know. Now we had sort of somewhat simplistic theory, which sort of claims that actually all but what happens is sort of the same as in the Kohl-Hopf line. I mean, when you're here, you're moving sort of along the line for this given x and then end up on the diagonal. Okay, whether this is really true, I mean, this has to be sort of studied in more detail. And so what I want to show you in the last few minutes is just briefly, our numerical evidence. I mean, by this is sort of the correct general picture. So this will go very quickly. Okay. Okay. So what is plotted over here? I mean, you should look at this one is the static correlated. So this is the independent case, and this is sort of now just the delta peak. But when we go away from the diagonal, I mean, then you see that correlations appear. Right? I mean, so, but they are short range. You see, these are a few lattice sites here. Okay, and then you see that the scaling functions are sort of well, I mean, these sort of for different values of y. I mean, you sort of see these scaling functions. I think I just wanted to show you this picture really. That as I go away from the diagonal, I mean, nothing really drastic is happening. Okay. And I guess this is the same picture at the different value of x. And again, I mean, our claim would be that if I sort of superimpose these things for different values here, I mean, this one and this one, they should coincide. And this, I think, we have plotted here in the next picture. Okay, here you see, trying to sort of, see whether it's a good scaling plot. I mean, it's at fairly short times, and maybe with I mean, the Schmidt and company never went away from the Popkov-Schütz model. I mean, so we don't know what their simulation would give, and maybe they are doing some simulations in order to also check this. Okay, yes, so that's I guess just a moment.
Yeah, the standard exponent seems to work well, no?
Yeah, but you see, I mean, it has this criticism that we are looking at too short times. I mean, and then with this kind of it's correct. I mean, with this sort of precision, I mean, you could say I mean, if the exponent changes, it's not a dramatic change, right? I mean, so anyway, so this is the end of the story, and so thank you very much for listening.
Okay, thank you very much. We have time for questions. Please, Deepak.
Is there any way to define renormalized hopping rates for this problem?
What do you want to define?
Under coarse graining, how does the hopping rates change?
Well, yeah, we looked at this a little bit, and so this is a slightly more complicated story. I mean, okay, so details, I mean, you have to look up, but I mean, just to answer the question, I mean, so what we argued is that, which maybe is a little bit, okay, you see, there are two terms here which live on very different scales, right? I mean, this one is sort of the microscopic scale, which tells you what sort of the noisy fluctuations locally, and this is sort of a more global scale here. And we argued that these two coefficients, x and y, because both of them are sort of eventually on the global scale, and the rescaling will not change. However, what we took into account, and which sort of confirms this picture, is that if I do the rescaling, of course, this will not become, this will be no longer equal to 1, because, I shrink the space, and that will change the diffusion coefficient. Okay, so we did, some sort of primitive coarse-graining argument, which sort of seemed to confirm our picture, but, it's up to improvements.
Herbert, if you go from 2 lanes to 3 or higher lanes, do you think the university
well,
will still...
no, you see, on this level, it's sort of, well, okay, I mean, you want to have 3 and all the same velocity, or
For instance,
no, okay, I mean, so 3, I mean, you have, of course, you can have 2 sort of sitting on top of each other. Yeah, no, we never really seriously looked at that case. You see that there's one problem in this area is that, the idea that, just looking at the general case, I mean, just count the numbers, I mean, so, the free parameters increase very quickly, right? And then it becomes sort of a little bit, which case do you really want to study? And sort of, at the beginning we were sort of also naive and thought maybe one can do something more general, but it was very nice actually to have, this real applications of these models and which sort of indicates which kind of parameters might be interesting. Yeah, no, we never looked at. Yeah.
A long time ago we studied essentially this model in the case where average phi1 and average phi2 are non-zero, which means you have linear wave-like couplings between the two. And in that model, if you inverted the signs of some coefficients, you have an instability. Is the instability when xy product is negative the same as that instability? Is there a, do you get a coarsening?
That's a good question. Yes, okay, let's see. So what, let me first explain my understanding of
Right.
what the instability is, right? You see, at least of the way I looked at it was that I said, okay, what we should look at is first the issue of the stability of the deterministic quadratic term. And there is a notion of sort of for hyperbolic conservation laws, sort of, what they call sort of stable systems. And the answer is that when you look at, let's see, how should I say? I mean, okay, maybe I cannot explain it so quickly, but I mean, there's a certain coefficient which you have to work, which sort of, must have sort of real eigenvalues. Okay, I mean, there's a condition for stability of the system, and the simplest, the simplest case of an unstable system is actually when you just take, just take the linear term. And then if you make the coefficients...
Yeah, no, that's the case I was talking about.
Okay,
and that's the case that we studied a long time ago. And there is an instability there, and the system coarsens.
Yeah.
But is the character of the instability the same when you have an instability, coefficient mismatched only in the nonlinear terms as here?
Yeah, I worked out the stability criterion for this case, and then the answer is that it's sort of satisfied only if x times y is strictly positive.
Right.
And when I look at the Weinberger, I mean, he also sees this coarsening, and then also the Kadar already noticed that his simulations was running not so well, and so I think it's presumably, at least sort of, loosely related to what you are mentioning.
Right. Yeah. Sorry, one other just elementary question. Finally, as far as Z goes, are you coming down in favor of 1.5 if you study on long enough time scales, or do you really think there's a 1.4 something?
Well, it's open future. I'm sort of, I don't want to. But what I believe would be nice if people sort of do this functional type of renormalization, and then this sort of looks to me like a method which might be able to get sort of more substantial, rather than having beliefs and some. Okay.
Okay, so let's thank Herbert again.